Show you how to work some problems involving calculating acceleration. Now, you don't necessarily have to know this, but this is only for cases of constant acceleration. When the acceleration is the same the whole way through, this method does not work if it's not constant acceleration, but fortunately for you, most of the things you're going to encounter in my class, in fact, all of them, will be constant acceleration. So let's see how to work these, and first we need a situation. And when thinking about acceleration, the thing that comes up most often is acceleration times for cars. And I drive what could by no means be considered a hot rod ever. It's just your standard small car. It's a 2006 Kia Rio. And using a website called 0to60times.com, they have for just about any make and model you could imagine how long it takes that car to get from 0 miles per hour to 60 miles per hour. And so I've looked that information up, and here's what we have. A 2006 Kia Rio will go from 0, and I'm going to convert these speeds to meters per second, 0 meters per second, to 26.82 meters per second, that's 60 miles per hour, in a time of, wait for it, 9.8 seconds. That's right, that's the hot rod I'm cruising around in. So, using this information, we want to find the acceleration. And in order to do this, we're going to set the problem up like you know how. First, we start with what we're given. And so we see that we're given 3 numbers relating to the motion of the car. We have 2 speeds and a time. And when we're dealing with acceleration, it's very important that we distinguish between what was the time when we started paying attention and what was the speed when we started paying attention and what was the speed when we finished. At the beginning of this situation, when we first look, the car is traveling at 0 meters per second. So that's our initial velocity. So we would say initial velocity, there's that subscript I, is equal to 0 meters per second. At the end of this whole thing, once we finally get up to 60 miles per hour, our final velocity will be 26.82 meters per second, and the time that it took was 9.8 seconds. Notice how I've taken the time on all of these to write units, and these units, a unit of distance over time, tells us that this is a speed, but I've also listed exactly what kind of speed. This is the initial velocity. I want you to label everything like this because that will become very, very handy later on. All right, next, what is it we want? We want acceleration. And so we're going to use the acceleration equation in order to find this. And that is acceleration is final velocity minus initial velocity over time. And now we're going to plug in what we know. We know our final velocity is 26.82 minus 0 divided by 9.8. And when working these, one of these won't always be 0, so it's not like the initial velocity will always be 0 or the final velocity will always be 0. They'll always be 2 numbers, and they could be any numbers, doesn't matter what. So when you're solving this, the first thing to do is actually to simplify the numerator of that fraction. So just take this subtraction problem and work it first. So 26.82 minus 0 is 26.82 divided by 9.8, and now this is just a simple math problem, 26.82 divided by 9.8, which gives us an acceleration of 2.73. And now let's talk about units for a second. Up in the top of this, we've got a speed minus a speed. And so the units that we get on top are units of speed. Meters per second. And on bottom we have time, which is per second. So we would say this as 2.73 meters per second per second. So that tells us that for every 1 second of time that passes, this car can increase its speed by 2.73 meters per second. Now this is kind of ugly to look at. So we have a way of simplifying that. When you have multiple fractions like this, the ones on the bottom can combine, and so we can say this is 2.73 meters per second squared. And if you're curious as to exactly where that comes from, let me know, and I can show you the details of the math if you're really into fractions. If not, and you can just remember that, I have no problem with that. So there's how we'd set up and solve one of these acceleration problems. We're going to look at another example now where we're finding some other piece of information, namely the time. So another example, but this time we'll take a fast car, why not, and use this car's information. So I grew up, my dad is a muscle car fanatic, so when I saw that Dodge was releasing these a couple years ago, it was kind of exciting. So a 2011 Dodge Challenger, and I chose specifically the fastest model, or the quickest model I should say, because hey, why not? We'll accelerate at 6.10 meters per second squared. Now, if you'll recall, my poor little Rio will only accelerate at 2.73 meters per second squared. So this car will accelerate almost 3 times as quickly as mine. It's a lot of power. Would love to get a chance to drive one of these if anybody out there wants to send me one. All right, 2011 Dodge Challenger will accelerate at 6.1 meters per second squared. How long will it take to go from rest to 26.82 meters per second? So remember, that's 60 miles per hour. So here's how this is framed. We know the acceleration. We want to know how long it will take, how much time will pass to go from rest to 26.82 meters per second. Notice it says from rest. Anytime you see something as being at rest or starting from rest or coming to rest, what that means, rest means not moving. 0 meters per second of speed. So that's just a fancy way of saying that. All right, we're going to set this up just like we did the other one. What are we given? What do we want? We're given an acceleration of 6.10 meters per second squared. We know it's an acceleration because of the units and because it told us. So we have multiple hints there. And now let's take a look at these speeds. 0 meters per second, 26.82 meters per second. We have to think about which one we're starting at. How long will it take to go from rest? That must be where we're starting at. So our initial velocity is 0. Going to 26.82, that must be our final velocity. And in fact, it is. And we want the time. So just as before, we set up our equation. Acceleration is final velocity minus initial velocity over time. And now we plug in what we know. The acceleration is 6.10. Final velocity of 26.82, initial of 0, and we don't know the time. And just as before, I still recommend that the first thing you do is get rid of this problem in the numerator. Don't leave fractions any longer than you have to. They're a good way to get yourself confused. So 6.10 equals 26.82 minus 0 is 26.82. And that's divided by time. Now remember, I said don't leave fractions any longer than you have to. In order to get rid of a fraction on one side of an equation, multiply by the numerator, or the denominator rather, and that will cancel both sides out. So I multiply both sides by t, and I'm left with 6.10t equals 26.82. And now we are a short division problem away from knowing our answer. So 26.82 divided by 6.10 gives us a time of 4.40 seconds. So a 2011 Dodge Challenger, and remember this is the tricked out model, will go from 0 to 60 in 4.4 seconds, which is remarkably fast. All right, things to remember: make sure you label everything properly. Make sure you're finding the initial and the final speeds, and you'll have to read the problem very carefully to know which is which. And then make sure you're writing out the equation and then substituting values in, making sure to deal with this fraction first. Do all that and you should be okay.